Hello students, the wave equation for lossy dielectric medium we already derived. Next is solution of wave equation for lossy dielectric medium. So wave equation for lossy dielectric medium is d square by dz square minus gamma square into ex of z is equal to 0. This gamma we know that is propagation constant, and in this it is a linear homogeneous differential equation, and its solution is ex of z a e raised to gamma z plus b e raised to minus gamma z. So we already in maths we studied the solution of this differential equation should be this. Here where a and b are constants. So in our case, the field must be finite at infinity. It requires that this a is 0. So this component becomes 0. And also this wave is propagating along az direction. This e raised to gamma z, that means the wave is propagating along minus az direction. This represents the wave is propagating along minus az direction. But in our case, the wave is propagating along plus az direction. So only this component is existing, that is b e raised to minus gamma z. So in this equation we introducing or inserting the time factor e raised to j omega t. So in this equation we are inserting the time factor e raised to j omega t. So we can write it as e z of t will be equal to ex of z into e raised to j omega t ax, because we are considering only the x component of e of z. So ex of z e raised to j omega t ax. And in this equation, the real component of this equation only we are considering. So we are taking real component of this equation. In this, we are going to substitute equation, the ex of z, that is solution of this differential equation. We are substituting ex of z. We know that we already written ex of z as b e raised to minus gamma z. This gamma is the propagation constant, we know that, and this propagation constant gamma we can take it as alpha plus j beta, and this alpha and beta are another constants that we defined later. So here this propagation constant we can take it as alpha plus j beta. So substituting the ax of z in this equation and substitute the value of gamma also here. So we will get this again, this real part of ex of z can be written as b e raised to minus gamma z e raised to j omega t ax. Now we can substitute the value of gamma here, that is again real part of b into e raised to minus alpha plus j beta into z e raised to j omega t ax. Now rearranging this equation, this e raised to alpha z and the e raised to j term we have to combine and we had to write it. So this equation again becomes real part of b into e raised to minus alpha z Again, e raised to j part, e raised to j into, that is omega t minus beta z ax. In this, so in this equation, we know that this e raised to j omega t minus beta z, that if we taken as e raised to ja, that is, we know that e raised to j is cos of a plus j sin a. So this equation we can again written as, that will be equal to real part of e z of t will be equal to real part of b e raised to minus alpha z. This e raised to j omega t minus beta z can be written as in this form, that is cos of omega t minus beta of z plus j sin omega t minus beta of z into ax. So here we only require the real part. So again this equation becomes b e raised to minus alpha z cos omega t minus beta z into ax. And this is the equation for the electric field intensity. That is, E z of t will be equal to b e raised to minus alpha z cos of omega t minus beta z dx. So here only we are taking the real part of this component. So we are taking this cos of omega t minus beta z. And this is the solution of the electric field intensity, that is b raised to minus alpha z cos of omega t minus beta z ax. And in the question, if the solution, derive the solution for the wave equation for electric field intensity, then you have to derive up to this. If you want to find the solution of the wave equation for the electric field intensity, we have to derive up to this. Similarly, we can derive the solution for the magnetic field intensity also from our Maxwell equation. So again from the third Maxwell equation, from third Maxwell's equation, we can write it as del cross Es will be equal to minus j omega mu Hs. This is our third Maxwell's equation. So this, from this equation, the left hand side, this is del cross Es. This we can write it as, expand this term, and we can write it as determinant of, this is curl, so we can write it as Ax, first row becomes Ay, Az, and the second row becomes dou by dou x, dou by dou y, dou by dou z, and the third row becomes the component of Es, that is Exs, Eys and Ez. Now again this become right hand side is, we can expand and we can written as j omega mu into this component of Hs, that is Hxs Ax plus Hys Ay plus Hzs Az. And we already know that the wave is propagating along z direction. So dou by dou x, which is equal to dou by dou y, which is equal to 0. So wave is propagating along z direction. So x and y component will be act as constant, so it won't change with the time. So this dou by dou x and dou by dou y will be 0. X and y component will not vary. So this dou by dou x and dou by dou y will be 0. So in our determinant again can be written as determinant of ax, ay, az. This dou by dou x becomes 0 and dou by dou y becomes 0, and remaining is dou by dou z, then exs, eys and ezs. Again this will be equal to, the right hand side is minus j omega mu hxs ax plus hys ay plus hzs az. Now we expand this determinant and equating both sides the ax components. When we expand the determinant, we get the first term as minus 0 minus dou by dou z of eys into ax, then minus of 0 minus dou by dou z of exs into ay plus 0 into az, and the right hand side becomes minus j omega mu hxs ax plus hys ay plus hzs az. Now we equating on the both sides the ax components, equating ax components on both sides. So we will get dou by dou z of eys will be equal to this j omega mu hxs. That we take it as equation number 1. And similarly this ay components we are equating on both sides, equating ay components on both sides. So we will get dou exs by dou z will be equal to minus j omega mu hys. Now again if you take this eys from equation 1, let we are taking eys, the y component of the field intensity associated with the wave propagation in minus z direction would be, or z direction would be, eys is ey max e raised to gamma z. Let we are taking this component of the electric field intensity ey is taken as ey max e raised to gamma z, and we are taking the partial differential of this eys, so it will be dou by dou z of eys will be equal to, when we take the partial differential on this side also, it is dou by dou z of ey max e raised to gamma z. So that becomes Ey max into gamma e raised to gamma z. So this will be again written as dou by dou z of Eys will be equal to gamma into Ey max e raised to gamma z. And this Ey max e raised to gamma z, we know that is Eys. So again this dou by dou z is written as Eys is written as gamma Eys. That will be taken as equation number 2. Now we substitute the this equation number 2 in our equation number 1. Substitute equation 2 in equation 1. So we can written as this gamma dou by dou z of Eys is gamma Eys. So the first equation becomes dou by dou z of Eys is gamma Eys will be equal to j omega mu hxs. Now if you take Eys by hxs will be equal to j omega mu by gamma. Eys by hxs will be equal to j omega mu by gamma. Again this can be written as in square roots, that is j omega mu the whole square by gamma square. Only for deriving the equation we are taking the square and square root. Okay, but this both are same. So again this equation can be written as j omega mu the whole square. And we already know that what is gamma square, propagation constant, and already we define what is gamma square as, that is j omega mu into sigma plus j omega epsilon, that we already derived. So write the value of gamma square here, that is j omega mu into sigma plus j omega epsilon. And so this numerator, that is square, the denominator j omega mu is there. So again this equation becomes Eys by hxs will be equal to square root of j omega mu divided by sigma plus j omega epsilon. And this Eys by hxs, when we consider, this can be Ey by hx will be expressed as in terms of Ohm's law. This term can be expressed in Ohm's in terms of this term, that is Ohm's law, we can express it in terms of this electric and magnetic fields. That we can find now how we can express these two in Ohm's law. That is, E is, we know that electric field intensity E is, we know that is potential per distance, that is volt per meter. And this magnetic field intensity H is expressed in ampere per meter. Ampere per meter. Now we taking E by H, what becomes, that is volt per, E is volt per meter per H is ampere per meter. So this meter and meter cancel. So this E by H becomes volt per ampere. This E by H become volt per ampere. This represent the it is the unit is ohms. Volt per ampere is ohms. So this is the, in this case this E by H ratio is known as intrinsic impedance. This ratio is known as intrinsic impedance, and its unit is ohms. This E by H is known as intrinsic impedance. So its value is this, that is intrinsic impedance can be represented as eta, and this eta is equal to Ey by Hx, and that will be equal to, that we already derived now, that is j omega mu divided by sigma plus j omega epsilon, and this is a imaginary term is there, and this value can be written as its real part is eta and its angle is theta eta. It is a complex value because this is a complex value or complex number. So this can be written in polar form as eta, magnitude of eta, and angle theta of eta. And this term is very important, this intrinsic impedance. Its value is Ey by Hx, and its unit is in ohms, and that will be equal to, the value of this intrinsic impedance is equal to square root of j omega mu by sigma plus j omega epsilon. In polar form it is magnitude of eta, angle theta of eta. So again we can say that if E of z of t, for intensity z of t can be that will be b is equal b into e raised to minus alpha z cos of omega t minus beta of z ax. That is equation number 5. Then our H, magnetic field intensity, can be written as, if E is this one, so intensity, magnetic field intensity becomes B by eta e raised to minus alpha z cos of omega t minus beta of z minus of angle theta of eta, and in AY direction. That is, from our equation we already derived, that is Eys by Hx is equal to j omega mu by sigma plus j omega epsilon, that we already defined, that as it is becomes the eta intrinsic impedance. So the magnetic field intensity solution will be written as B by eta, or it is intensity E by eta. So that is again equal to, the value of E becomes B raised to minus alpha z cos omega t minus beta z, and divided by eta. Eta value is magnitude of eta and angle is theta eta. When this angle comes to the numerator, it is minus theta of eta. So our solution of this magnetic field intensity is this. Now at free space, the value of intrinsic impedance, that is eta 0, that we can find out. So at free space we know that the value of this j omega mu divided by value of the interconductivity sigma is 0 at free space. So j omega mu by sigma is 0 plus j omega epsilon. So this becomes again this j omega mu divided by j omega epsilon. This j omega cancel. So at free space eta 0 is equal to square root of mu by epsilon. So at free space mu is mu 0 and epsilon is epsilon 0. So this become mu 0 and epsilon 0. So when we substitute the value of mu 0 and epsilon 0, we will get intrinsic impedance at free space as 120 pi, or its value is 377 ohms. And this value is very important. The intrinsic impedance at free space is 120 pi, or it is equal to 377 ohms.